Welcome back to our lecture series on structural characterization of materials. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In the previous lecture, we saw that the electron source is the most critical component of a scanning electron microscope because it fundamentally determines the brightness, stability, and energy spread of the electron beam. We studied thermionic emitters in detail and also briefly introduced field emission sources. Building directly on that foundation, this lecture focuses entirely on field emission electron guns. We will examine how electrons are extracted from an extremely sharp tip using strong electric fields and how quantum tunneling rather than thermal excitation governs the emission process. By understanding the physical mechanism of field emission in detail, we will see why these sources produce highly coherent, high brightness electron beams, why they require ultra-high vacuum conditions, and why field emission SEMs consistently outperform thermionic sources when high spatial resolution and beam stability are required. There are three different types of field emission electron sources: cold field emission (CFE), thermal field emission (TFE), and Schottky field emission (SFE). The figure on this slide illustrates the potential energy barrier at the emitter surface and how it is modified under these three emission conditions. The vertical axis represents electron energy, while the horizontal axis represents the distance from the emitter surface into the vacuum. The curve labeled CFE corresponds to cold field emission, where electrons tunnel through a strongly thinned barrier. The TFE curve represents thermal field emission, where moderate heating assists field-induced tunneling. The SFE curve corresponds to Schottky field emission, where surface engineering and the applied electric field lower the effective emission barrier. Although all three involve field-assisted emission, the shape of the barrier and the emission mechanism differ. We will examine CFE, TFE, and SFE individually in the following slides. Let us now focus on cold field emission and first establish the basic physical picture before looking at quantitative details on the specific gun geometry. In cold field emission, the electron source is an extremely sharp metallic tip, typically with a radius of curvature of only a few nanometers. Because of this sharp geometry, any applied voltage leads to a very strong concentration of electric field at the tip apex. This intense local electric field fundamentally alters the surface potential barrier at the emitter vacuum interface, creating conditions under which electrons can leave the metal without requiring thermal excitation. As a result, cold field emission produces an extremely small effective source size and a highly coherent electron beam. But it also makes the emission strongly dependent on surface condition and vacuum quality. With this qualitative picture in mind, we can now look more closely at how strong the field must be and how the potential barrier changes to enable electron emission. As the electric field at the emitter tip continues to increase, it can reach magnitudes on the order of 10 volts per nanometer. At such high fields, the surface potential barrier at the metal vacuum interface is significantly reduced in height and compressed in width. Under these conditions, electrons no longer require thermal energy to escape the metal. Instead, they can tunnel directly through the narrowed barrier and leave the cathode by a purely quantum mechanical process. The figure illustrates this effect clearly. The left side corresponds to the metal and the right side corresponds to the vacuum. As the applied electric field increases, the surface barrier becomes progressively thinner, allowing electrons near the Fermi level to tunnel into the vacuum. This field-driven tunneling mechanism is the defining feature of cold field emission. It explains why CFE sources can produce an extremely small virtual source size and very high brightness, even though the emitter operates at or near room temperature. At the same time, because the tunneling probability depends very sensitively on the local electric field and surface condition, cold field emission is also highly susceptible to surface contamination and therefore requires excellent vacuum quality for a stable operation. In cold field emission sources, tungsten is most commonly used as the cathode material. This is primarily because tungsten has excellent mechanical strength, which allows it to withstand the extremely high mechanical stresses produced at the tip by the intense electric field. In addition to tungsten, other materials have also been explored for field emission. Carbon nanotubes and silicon nanotips, for example, have been employed quite successfully because their extremely small tip radii allow very strong local electric field enhancement. One of the most important consequences of cold field emission is the very high cathode current density that can be achieved. Using a field emitter, current densities as high as 10 to the power 5 amperes per square centimeter are possible. For comparison, a typical thermionic electron source produces a cathode current density of only about 3 amperes per square centimeter. This dramatic difference highlights why field emission sources can deliver much higher brightness and superior performance in high-resolution SEM applications. In a cold field emission gun, two different voltages play distinct and independent roles. The first is the extraction voltage V1 applied between the emitter tip and the first anode. This voltage determines the local electric field strength at the tip apex and therefore controls the ability of the electrons to tunnel out of the cathode. Typically, an extraction voltage in the range of 3 to 5 kilovolts is sufficient to generate emission currents on the order of 10 microamperes. Increasing V1 primarily affects the emission current, not the beam energy. The second voltage is the accelerating voltage V0 applied between the emitter tip and the grounded second anode. This voltage determines the kinetic energy of the emitted electrons and therefore sets the beam energy used for imaging. The accelerating voltage can be varied over a wide range, from a few hundred volts up to about 30 kilovolts, depending on the SEM operating conditions. The key point is that in a cold field emission gun, electron extraction and electron acceleration are controlled independently. This separation allows precise control over emission stability and beam energy, which is a major advantage of CFE sources. Cold field emission places extremely stringent requirement on the cleanliness of the cathode surface. For a stable operation, the emitting tip must be atomically clean because even a very small amount of absorbed gas can strongly affect the tunneling processes. To appreciate how severe this requirement is, note that even at a vacuum level of 10 to power minus 5 pascals, a complete monolayer of gas molecules can be deposited on the tip every second. For this reason, sustained cold field emission operation requires ultra-high vacuum, typically in the range of 10 to power minus 8 to 10 to power 9 pascals. Before operation, the emitter tip is therefore flashed clean by briefly heating it to a temperature of about 2500 Kelvin for a few seconds. This removes adsorbed gases and restores a clean emitting surface. Immediately after flashing, the emission current is typically very strong, but it decays over the next 10 to 15 minutes as gas molecules again begin to adsorb on the tip. Once approximately a monolayer has formed, the emission stabilizes and can remain relatively constant for several hours. Eventually, further adsorption leads to renewed instabilities and the tip must be flashed again. Each flashing cycle causes the tip to become slightly blunter, and after many thousands of flashes, the available extraction voltage may no longer be sufficient to reach the desired emission current. However, since a tip is typically flashed only once per day, this blunting process is very slow. As a result, the useful lifetime of a cold field emission source is extremely long, often extending over many years. In cold field emission, we saw that achieving extremely high brightness and coherence comes at the cost of very strict vacuum requirements and sensitivity to surface contamination. This naturally leads to the question, can we retain the excellent beam properties of a CFE source while relaxing some of these operational constraints? This is where the thermal field emitter or TFE comes in. A TFE has essentially the same emission properties as a cold field emitter, but it is operated at an elevated temperature. The primary role of this additional heating is not to drive thermionic emission, but to keep the emitter tip clean by reducing the buildup of adsorbed gas molecules. As a result, TFEs exhibit lower noise and improved emission stability, even when the vacuum quality is not as extreme as that required for CFE operation. An important point is that a TFE can also be operated for short periods in a cold field emission mode by lowering the temperature. This flexibility makes TFEs particularly attractive for practical SEM operation, offering a balance between performance and robustness. In a Schottky field emitter, electron emission occurs by a mechanism known as field-assisted thermionic emission. Unlike cold field emission, the applied electric field here is not primarily used to strongly narrow the surface barrier for tunneling. Instead, a moderate electric field is applied to lower the effective work function of the emitter through the Schottky effect. At the same time, the emitter tip is coated with zirconium oxide on a flattened tungsten surface. This coating reduces the intrinsic work function of tungsten and improves the chemical and mechanical stability of the emitting surface. The combination of moderate heating, reduced work function from the zirconium oxide coating, and field-induced barrier lowering allows electrons with sufficient thermal energy to escape into the vacuum efficiently. Although the Schottky field emitter is fundamentally a thermionic source, the emission area remains small and well confined. As a result, its brightness and emission current density are comparable to those of a cold field emitter, while offering much greater operational stability and relaxed vacuum requirements. So far we have discussed different types of electron sources and how electrons are emitted from the cathode. To understand how these sources ultimately affect imaging performance, we now introduce a key quantity known as electron source brightness. Brightness describes how much electron current can be delivered from a small source area into a small angular range. In other words, it tells us how tightly electrons can be packed in both space and angle. Mathematically, the brightness beta is given by beta equals 4 times the beam current divided by pi squared, the square of the source diameter and the square of the beam half angle. Here IB is the beam current emitted by the source, D is the effective diameter of the electron source, and alpha is the angular spread of the beam as it leaves the source. This expression immediately shows why brightness is such a powerful matrix. Increasing current helps, but brightness increases dramatically when the source size and angular spread are reduced. This is precisely why field emission sources, which have extremely small source sizes and narrow angular distributions, exhibit orders of magnitude higher brightness than thermionic emitters. High brightness is essential for forming a small probe with sufficient current at the specimen, which directly translates into higher spatial resolution and improved signal-to-noise ratio in SEM imaging. Now that we understand what electron source brightness means, we can compare how different field-based electron sources perform in practice. This table summarizes the key differences between cold field emission, thermal field emission, and Schottky field emission sources. In cold field emission, electrons are emitted purely by quantum tunneling from an atomically sharp tip at room temperature. Because the source size and angular spread are extremely small, CFE provides the highest intrinsic brightness, typically around 10 to power 8 to 10 to power 9 amperes per square centimeter per steradian. However, this comes with poor stability and very strict ultra-high vacuum requirements. In thermal field emission, the tip is operated at an elevated temperature. This helps maintain a clean surface and stabilizes emission at the cost of a modest reduction in brightness. TFE therefore offers a practical balance between high brightness and improved stability. In Schottky field emission, a heated tungsten tip coated with zirconium dioxide emits electron by field-assisted thermionic emission. Although the intrinsic brightness is lower than that of CFE, Schottky sources provide excellent beam stability, longer lifetime, and more relaxed vacuum requirements, which makes them widely used in analytical SEM. Overall, this comparison highlights an important trade-off. CFE maximizes brightness, TFE balances brightness and stability, and Schottky sources prioritize robustness and reliability while still maintaining high performance.